Okay, so good morning, everyone, and I really appreciate to invite me to this very nice forum. And actually, I'm not working on like a machine learning thing yet, but I just want to show one like research field. Maybe machine learning, computational research can be applied very well. So this is about like high pressure based research, and also this time I just want to introduce what I'm doing, also what I'm interested in like a multi-extreme condition of material science. Okay, so so actually, because I was lazy, so I just put only my name, but it's based on the collaboration with my institution and the Stanford and the postdoc in Korea and the University of Cambridge, where I was put it a postdoc a long time ago. Okay, so basically, we are interested in like a universe and in space science. So what kind of material and what's the planetary science can be exist there? Then, and it consists of like a multi-extreme conditions there. So each to be more like a pressure and temperature, also high irradiation states like a cosmic rays comes down. And as you all knows, I mean, so these days many countries involved, including like the United States and China, also Korea and Japan, they interested in it's like a terraforming in other planets. So we should understand what's behind and below there. Also, what kind of material we can use to utilize for our daily life there. Okay, so we gathered some. I mean, this is the experimental part. So I'm doing computational work, by the way. So we gathered like a high pressure center with the high pressure and the high magnet and plasma and nuclear reactor and like a pulsar electron beam, so on. So we're trying to gather all these multi-extreme conditions into like in situ situation. So condition. So to kind of torturing material to undergo some phase transition and to understand what's going on there. So we had several workshops, and this is between the Koreans and now, so we gather like China, Korea, Japan. So like this multi-extreme condition scientists, we all gathered. So we are continuing to make some big consortium in these directions. So this is one of the like proposals in United States. They proposed some time ago, but which was not successful yet. But in this like in Oak Ridge National Lab, for example, they want to establish like a very high magnet, like a 25 Tesla, and like a pulsed field, and set to 40 Tesla and around 100 GPa pressure and so on. So also very low and very high temperature. So if you can combine all these extreme conditions, so what can happen? So for material science, so that should be very, very important and very interesting research subject from now on. And so actually I'm working on that direction, but also it's very good for research field. We can apply machine learning research there. So this is a very schematic idea. So how if you pressurize material, and also, I mean, this is under pressure material, for example, and if you put some like a beam, like a high irradiation happen, then in this sample, so this is a equilibrium phase diagram, for example, and if you apply this non-equilibrium path like high irradiation or some very rapid dynamics, then this phase diagram can be much distorted. And if once we recover this high pressure material back to ambient, then maybe we can stabilize this material at ambient conditions. So this is a non-equilibrium path. So we try to find some new material which only exists only at high pressure, but which can be recovered back to ambient conditions. Okay, so let's just focus on high pressure, because I'm talking about multi-extreme case, but actually my major is high pressure. So this is because I think you don't have that much backgrounds for high pressure research. So simply just saying, like this is like a pressure dimension, let's say. So these days people trying to go to 1 terapascal pressure range, but usually they end up to here. And around like 10 GPa. So 10 GPa is kind of the pressure where the silicon bond change disorder, like from sp3 bonding to sp2. So silicon turn into metallic state. And around the 100 gigapascal, then the carbon turn its bonding state to like sp3 type. So diamond, so sp2, like graphite structure can turn into diamond structure there. And around the 300 gigapascal, maybe you heard about this, like these days, room temperature superconductivity in hydride system, maybe several Nature papers comes out there. So that can be related to this pressure range. And 500 gigapascal around then is only very rare cases in the world. They report to reaching this pressure. And then on this pressure, we can see the metallization of solid hydrogen. So because solid hydrogen can turn into metallic state, then it's become the very high TC superconducting material. And we believe that actually interior of Jupiter should consist of this metallic hydrogen, and it's a very high superconducting state there. So could it be related to high pressure, but also related to the planetary science? Okay, so under pressure, actually, this is superconductivity and superionicity and the superoxide and the electrolyte, some very interesting keyword can like very naturally can occur in this high pressure conditions. So, so these days you heard about this like a superconductivity, like room temperature one and high pressure, and superionicity. Maybe you heard about this, like ice also can into superionic state at high pressure. Some like Neptune and Uranus can have such a state. And also we published some maybe also in the deep low matter maybe has some like a superionic state and superoxide. So this is one of the kind of air battery application. It was one of the hot issue before. So superoxide also could very naturally occur in high pressure conditions. So could be related to that. And this phenomena actually they are linked to each other. So this is one thing I want to explain today. Okay, so I'm doing like a high throughput calculation, DFT-based crystal structure prediction, so on the high pressure. So these materials, what I predicted during the last years, and except this one, like 2D silicon, and all of them, they this prediction was found to be real. So, and actually, maybe this one could be more relevant to the material science community. But I didn't prepare any slides about this because when I just came here and I talked to other scientists and they shows much interest on this work. So actually I didn't know this part. So I just want to show one like a poster. So by Professor Haiqing Lu from Beihang University. So he cited our work and shows more details about that. So about this like a 2D like a ferromagnetic material, please come to his talk and his poster. Okay, this is not my work yet. Okay, so anyway, so I just let me just focus on this like a geoscience aspect because this is what I did most during many years. So this is one thing I'm very proud of. Okay, so last year actually we host one Nature conference called the Frontiers of High Pressure Research Science Under Extreme Conditions. In Shanghai. So we gathered lots of like nature editors and we discussed lots of things. So what can be the future of this extreme science? And actually the general consensus was that so hydrogen. So pressurizing hydrogen and hydride should be a good research directions at the end. So that's what we talk about this. So I switched my title a bit to change like when iron meets hydrogen. So this can be quite important question for geoscience. So let me explain how I addressed this question using a computational approach to this field. So these two, Dr. Yuha, Dr. Bo Gyujang is previously my postdoc, so they work in this field mostly, and then now they are professors in China and Korea now. So, okay. Let me start from the shortcoming of DFT. So maybe you know that actually DFT has a very big problem to describe in transition method the ground state. So DFT, okay, dense functional theory cannot predict this BCCF's space transition of iron, so which is partially occupied this state. So, but only very recently, actually, dynamic mean field theory, which can describe using many-body effect, and which can explain this is BCC state transition. I'm sorry. So, in 2018, by Christian Howley in Local University, they for the first time they succeed to calculate the total energy of a BCC F-space transition at finite temperature using dynamic mean field theory, and we successfully reproduce their data. So if you see this one, then you can see that. So at finite temperature, the BCC should be stabilized one, and this is a Bain pass about the C over A ratio. But DFT predict this FCC is stable, but in reality, the BCC is stable one. So this is correct description. Okay, so now we can use dynamic mean field theory. So at the time, I mean, a long time ago, I worked with Chris Pickard in Cambridge. So I quite used to this AIRS, which is high throughput structural prediction approach using CASTAP mostly. So how about this combining this dynamic mean field theory and this AIRS to describing this correlated system under pressure? Then maybe we can utilize this approach to predict this ternary phase diagram over this very, geologically relevant ternary compounds or binary compounds there. Yeah, so once we have this ternary phase diagram structural precision, then maybe you can calculate some other some electronic property, or so some dynamics of so on. So actually, let me describe one by one. So what I did. Okay, so this was the first paper we published a long time ago, and that time was quite shocking because people believe that this is hematite Fe2O3. So this iron and oxygen ratio is 1 to 1.5. So that was the most oxidized form of iron oxide. But under pressure, we predicted that with 100 gigapascal, FeO2 can exist, and experimentally very easily we synthesize it. So based on this structural prediction, and we try to explain that 100 gigapascals corresponds to the deep low mentor. So which can be much more oxidized in the oxygen concentration wise. Okay, that was a long time ago. And a year later or so, we found some isostructure FeO2 and FeO2H. So let me explain the crystal structure similarity between these two, and they are quite equivalent to each other. So they can explain the seismic velocity anomaly at ultra low velocity zone. So that was published a long time ago. So we were quite confident this FeO2 and FeO2H can exist at the deep low mentor, which is touching this Earth's core. So all this actually computational work except this the seismic velocity measurement. And this FeO2 and FeO2H, what I predicted in DFT was a pyrite type crystal structure, which is a very simple cubic structure. And this structure motif looks like this. So at FeO2 has this OO bonding, and this iron has equivalent distance to this two oxygen atoms. And when it comes to hydride, so it has a hydrogen here, then hydrogen located exactly in the middle of these two oxygen. So it has a very symmetric positions here. So only difference these two is the existence of this hydrogen position in the middle of two oxygen. And if you look very closely to this ternary phase diagram, so what I calculated a long time, actually, this was a very costly calculation. I did it like 7 or 8 years ago. And so if you see this, then this is iron and oxygen and hydrogen at 100 gigapascal. And in the center, this is FeO2H, and here is FeO2. So then you can see this along this line, there's many of them that can be stabilized or stabilized energetically, or they can stabilize like phonon can be stabilized, means like a metastable form. So along this line means I'm starting from FeO2H, so it can lose hydrogen and they can turn into FeO2 eventually. So that means the losing hydrogen does not change the stability of this crystal structure. So this is the side evidence. And so why this is symmetry is important is because this is what we found. I mean, in this FeO2H, which is pyrite type structure, it exists at a very high pressure, and at low pressure. Actually, this is called graphite, which is like a lost in your, I mean, in our daily life. So lost has this asymmetric bonding between oxygen and hydrogen, which has a covalent bonding. So hydrogen is very tightly bonded to oxygen, so it cannot release at all. But if you pressurize it, then this oxygen, I mean, hydrogen locates exactly in the middle of two oxygen, so it has an ionic bonding nature, and it can be easily diffused to the space. So we conducted ab initio MD simulation, and we found that so there are some partially melting state only. So why iron and oxygen vibrate harmonically by time, but only hydrogen start diffusing. So this is a superionic state. So only this proton diffusion is happening in this. So this is the MD result. And at the time, so we completed the phase diagram with the pressure and temperature and certain region in the middle, so between the solid and the melting. And we proposed the superionicity can exist theoretically, and people didn't actually convinced. So we combined with experimental data. So 2 years ago. And then experimentally, my colleagues, the Qingyang Hu, so he measured it. So then this is experimental data. So this is reciprocal temperature, and this is conductivity. So conductivity is suddenly increase in this pressure temperature region, and which is exactly correspond to this superionic contribution happen. So this is the evidence of this superionicity in our deep low mental. So we believe that so in our deep low mental, the superionic state of proton dynamics to happen. And in 2019, actually, the superionicity ice was proposed. So this one is about like Uranus and Neptune superionicity, but in our case, we are talking about our planet, the deep Earth. So we should have a superionic state. And also, there are many other candidates for these hydrous minerals in the deep low mental. So all these hydrous mineral, when it reach this deep low mental area, then it can turn into super ionic state. Okay, so only last year we also found the Earth's inner core, which has consists of mainly iron with a small amount of hydrogen or oxygen, carbon. Also can be a super ionic state as well. So which is a metal hydride is also can be turned into super ionic state. So the other papers on the review now is we are exploring why is a metal hydride system in iron hydride can be super ionic at high pressure. So it's because this is between the coupling between superionicity and the non-nuclear attractor. So this is an electrolyte effect. So this is electrolyte is popular phenomenon. So people are interested in. So we found in pure iron. So if we pressurize it, then around 100 gigapascal, then this O site is this beta net charge. So this is very simple dioptic equation. So O site can have a quite finite charge density, while this T site is losing charges. So this O site, this deviation generate the electrolyte effect in pure iron, HCP iron, and which can host this much electrons can host the pure hydrogen here. So this is MD simulation what we did, and this red dots, all this trajectory is about hydrogen diffusion and low pressure, and it's mostly stay at this electrolyte site, which is non-nuclear attractor site, and with the increasing pressure, it stay much longer time. So this is a summarized one, and at 100 and 150 and 300 gigapascal with the increasing pressure, during this MD simulation, this this is a kind of normalized time to hydrogen stay in this non-nuclear attractor, attractor electride site stay. So with the increasing pressure, this portion of staying in this site is increasing accordingly. So 300 gigapascal is stay much longer, around 80% of the time it stay at this non-nuclear attractor site. So means this electride is much enhanced and which is triggered at 100 gigapascal. And this may be important for understanding the difference between Mars and Earth, because Earth has inner core has around 300 gigapascal pressure, but Mars inner core has much less. Below 100 gigapascal the inner core pressure. So definitely, so iron hydride in Earth's core should have this super-ioning effect, but while the Mars doesn't have such effect. So we try to understand what can be related to the physical phenomena between this Mars and Earth inner core. So we can differentiate this inner state of the rocky planets. And this is one additional paper we published. We use dynamic repeat theory. And why I'm showing this one, this is why it looks quite simple crystal structure prediction, like a convex Soul graph between pure iron. This is pure iron. This is iron. This is pure oxygen. So this is a binary structural prediction, which seems quite simple. But this is a DFT plus DMFT structural prediction result. So this is an interesting one because with the pure DFT structural prediction, so actually the experimentally found one, which is the black colored this symbol, cannot be stable, cannot be the ground state. So this is at high pressure as well. So high pressure, we think this correlation effect can be much reduced. So maybe the standard DFT can work there, but it is not. So at high pressure, even at very high pressure range, so we need to include some correlation effect in this iron oxide system. So then if you correct by applying DMFT result, then we can now see this experimentally found can be stabilized energetically. So many-body effect is still important for describing high pressure materials especially for transition metal oxide system. And other information is too detailed, so just let me skip it. Okay, so conclusion is this crystal structure prediction is quite important, and hopefully this area can be applied to the. My next target is to using the machine learning approach to this high pressure research and structural prediction. Also, we plan to include other extremes like high irradiation. So in the case we need to include the TDDFT. Also, we need very serious DMFT level calculation. Also, there are also two ways to implement machine learning approach to DMFT. So like implicit solver, we can include the machine learning approach as well. So actually, we are working on that, but the progress is a bit slow there. So hopefully we can collaborate with others who knows this field very well, and we can think about some good science together. Okay, yeah, thank you very much.
Okay, thank you so much. So the talk is now open for question. Any question?
Yeah. Okay. So. Okay, so that was thank you for the question. So at ambient pressure, so this magnetic state, so it becomes the paramagnetic below this BCC space tension. So by temperature, so it's a magnetic BCC and turn to paramagnetic BCC first, and then turn into FCC, then turn back to this paramagnetic BCC again. So this is the phase diagram. So in this case calculation, we don't have to worry, think about this magnetic property.
It's about super ionicity during increased pressure, right?
Yeah.
They are really super ionicity. This any kind of experiment confirm about this?
Yeah. So maybe I was too fast. I'm sorry.
Uh-huh.
Yeah.
I think it's
Yeah.
most possibly it's
Oh.
about the amorphism.
No, actually, the space is gone. So sorry.
Uh-huh.
So yes, so I showed one graph which shows like the reciprocal temperature versus conductivity,
Yes.
and that was combined graph with the experimental data. So
Uh-huh.
certain area of temperature there was enhancement of conductivity, and which is experimental data with dots. And I can
Okay.
show you
Uh-huh.
later. And there below. Okay, this one. Thank you.
Okay.
So this is experimental data at high pressure, and this is our calculation data. So this is only when we considering electrical conductivity, and this is when we combine with ionic conductivity as well. So there is enhancement here, and which is also good match with this experimental data of this sudden increase of conductivity. So we believe this is evidence, the first evidence of this spirality of this iron hydroxide.
Okay, thank you.
Okay, any other questions? Even though, let's thank the Professor Kim again. Thank you very much for your nice talk.